All right, so this one is technically review from your first year chemistry course, but it's elemental composition of pure substances. So you should have gone through the difference between pure substances, mixtures, elements, compounds, etc. So hopefully you know all that stuff. If not, we'll figure it out along the way. So the enduring understanding's changed now. Now this one isn't actually about moles, it's about composition. So chemical formulas identify substances by their unique combination of atoms. So depending on how the atoms are bonded together, how many of each there are, it'll change the substance. So like water is always H2O, you know, that sort of thing. Carbon dioxide is always CO2. Learning objectives to explain the quantitative relationship between the elemental composition by mass. So we're going to learn composition by mass and the empirical formula of pure substances. So we'll figure that out too. Okay, great. Essential knowledge. Some pure substances are composed of individual molecules, while others consist of atoms or ions held together in a fixed proportion described by a formula unit. So in fixed proportions, held together is like water, so there's a pure substance because it never changes. You can have pure water. Gold, you can have pure gold. Oxygen, you can have pure oxygen. Carbon dioxide, you can have pure carbon dioxide. Salt, you can have pure salt. These are held together in fixed proportions, so these aren't actually a group of atoms. It kind of alternates in what's called a crystal lattice. That's why it's an ionic compound and not a covalent compound. That's not really actually part of this learning target. All you need to know is that a mixture cannot be pure. So if you mix salt and water, you get salt water, right? So this is a mixture of salt and water. Notice the plus. The plus is the and, which makes it a mixture. These all have a formula. So if it's a single formula, it's a pure substance. If you have to put an and in there anywhere, not a pure substance. Whoops, that was not supposed to happen. Be right back. There we are. All right, percent by mass. So you take the mass of the atoms of the element and divide it by the mass of the compound. So for this one, since there's two elements in there, we're going to need to do this calculation twice. Once for hydrogen, once for oxygen. So for hydrogen, if I can stand over here, slightly off screen, we have two of them. So you take 2 times whatever the mass of hydrogen is, which is 1.0078. I'm going to round that to 1. Then you divide that by the mass of the whole thing, the mass of water. Water has 2 hydrogens and an oxygen. That'll add up to 18 if you do the math. If you're not sure how to do the math, you add them up on your periodic table. So this is going to be 2 divided by 18, which is 1/9. And then you have to multiply it by 100 to turn it into a percent. I guess that should be in the formula here too. So this is going to be 1/9, which is 11.1 repeating percent. So water is 11.1% hydrogen by mass. Then for the other element, you can do this again, or you can subtract this from 100. Either way, you'll get the same answer. So for oxygen, there's only 1 oxygen, so I don't need to multiply it. I just take the number off the periodic table. The denominator should always be the same, because it's the same substance. Multiply it by 100, and you get 88.88 repeating, which will round up to 88.9% oxygen. So that's the percent by mass. So water is 11.1% hydrogen by mass and 88.9% oxygen by mass. All right, according to the law of definite proportions, the ratio of the masses of the constituent elements in any pure sample of that compound is always the same based on molar mass. So water is always 11% hydrogen to 88% oxygen. No matter what sample of water you have, that will always be true. No matter what sample of water you have, the formula will always be H2O. It'll always have the same molar mass. That is the law of definite proportions that says you always have 2 parts hydrogen, 1 part oxygen for water. They always weigh the same. Just know that, I guess. The chemical formula that lists the lowest whole number ratio of atoms in the elements in a compound is its empirical formula. Here's glucose, blood sugar. Sugar in your blood. You don't eat glucose, by the way. Your body processes most sugars into glucose. Anyway, glucose usually has 6 atoms of carbon, 12 atoms of hydrogen, and 6 atoms of oxygen. So if you notice, those are all divisible by 6. So if you do that, you get the ratio. 2 hydrogens to 1 carbon to 1 oxygen. This is the empirical formula. It's the lowest ratio between the elements. This is the molecular formula. This is the formula of the actual molecule. I could draw it for you. It's a hexagonal ring with hydrogens and oxygens attached to it. But this isn't the actual molecule. The molecule does not only contain 1 carbon. This is its empirical formula. The masses have that same ratio. So this is 6 times as many atoms. This is 6 times as much mass. So there's a 1/6 ratio in both the formula and the molar mass, which is fun. Compounds can have the same molecular and empirical formula. So carbon dioxide, that's a real molecule, so this is a molecular formula. And then you can't reduce that any further. That's already at the lowest ratio. This is sucrose, this table sugar. This is already at the lowest ratio because this 12 kind of throws it off. 11 is half of 22, of course, but 12 isn't half of anything in there, so you can't do any sort of division, kind of like prime numbers. Great? Great. Okay, then there's a 4-step process to calculate empirical formula from percent by mass. So if you get the percentages, like we just did, water's 11% hydrogen and 88.9% oxygen. If you're given that percent information, you can change that into an empirical chemical formula. So with this problem, we are given a certain percent of carbon and the remaining percent hydrogen. Percents are always out of 100, so you take 100 minus 84.2, and you'll get how much hydrogen there is. What is that? 15.8? So it's 15.8% hydrogen. Great. Okay, so we do this process. What you do first is you pretend that the percent is actually mass. So if it's 84% carbon, we're going to pretend that I have 100 grams of the substance, and then the numbers are really easy. It doesn't actually matter how much you have, because remember, if you have a little bit or a lot of it, it has the same chemical formula. So if you pretend that you have 100 grams, boom, I know exactly what 84.2% of 100 is. It's 84.2. So I start off by just rewriting the percent, but I'm just going to, instead of percent, I'm going to write grams, and then the elemental symbol carbon. Great. So then we convert that mass into moles. So that's what we did a couple learning targets ago. Hopefully you remember how to do this. Grams of carbon to moles of carbon. 1 mole is 12.01 grams. And you don't solve it yet. One thing about these is you have to do the steps one at a time for every element at the same time. So since I did this for carbon, I need to do this for hydrogen first. Otherwise, you're going to get lost. So 15.8 grams of hydrogen. Hydrogen's 1.01. 1.008, whatever. For percent by mass, you need to be a little bit better at not rounding. It just makes the numbers come out nicer because we have to deal with whole numbers and stuff, and it's mildly confusing if you don't use as many significant figures as possible. So usually you can round to the tenths place, but for these, hundredths place is probably better. Great, so we've done step 2 for both of them. They're both in moles now. I haven't solved it, of course. We should probably do that. Where's my calculator? Okay, so 84.2 divided by 12.01 is 7.01. And if I round, it's actually 7.0108. I'll round that to 0.7011. Try to keep at least 4 significant figures when you're doing this. Again, otherwise, when you do steps 3 and 4, you might not get whole numbers. And then you'll really be kicking yourself, scratching your head. And this one is 15.958. Okay, cool. Now we have these 2 numbers. Then you do step 3, divide by the lowest numbers. So which one's lower? This one, obviously. So this one's always going to be 1, the lowest number. You know, divide a number by itself, it's going to be the lowest number. And then this one is what? 2.27. .276. Okay, and then we need to multiply these until we get whole numbers. So you need to know your decimals pretty good. This looks like about a quarter to me. So I'm going to multiply all these by 4. So this is 4. Multiply that by 4, you get 10. So it's about C4H10. That's my chemical formula. So after step 4, you should get nice whole numbers or close to whole numbers, C4H10. Great? Great. Now it says our molar mass is supposed to be 114. So we need to check that. You take this puppy, see what its molar mass is. 4 times 12 plus 10 is 58. Hey, look, that's almost half of 114, right? I mean, there's some rounding errors that are happening here, but it's basically half. So what you do then is you double everything to get the molecular formula. So this is the empirical formula. It's the lowest ratio. How does that make sense? It's not the lowest ratio. Is 2.25 times 4 not 10? It's not 10. Oh, goodness. That's where the rounding error came in. 2.25 times 4 is 9. Cool, man. Turns out I'm not good at doing things without a calculator. So I get C4H9. This is good to know. All right, great. We're making progress here. So there's the empirical formula. What mass is that now? It's going to be 1 less, which will be 57. Ha! Now it's exactly half. Amazing. Okay. Good job, kids. Thank you. I'm sure you all knew that and were staring at me. It's good work. I'm not going to re-record the video. That would take too much time. Okay, so this has a mass of 57 now, which is exactly half of that. Great. We have our empirical formula. If you double it, you get the molecular formula. So C4 becomes C8. H9 becomes H18. Whew. Thank goodness we did it. Go team. And that's it. I believe that's it for the unit as well. Let's check. We're done. Great job.